Okay. So now we're going to look at, probably what we're going to do today is going to be mostly review of Science 9, and that is just naming simple binary ionic compounds. Maybe we'll get to molecular compounds, I hope so. Okay, but most of this will be a review. There'll be a couple of things in ionic compounds that will probably be new, but they're not yet. All right, now I gave you guys your periodic tables on Friday, right? Yeah. Okay, you're going to need those. You're going to want to have those out as well. Anybody not get one on Friday? Okay, first thing we got to review is the difference between an ionic compound and a molecular compound. What does an ionic compound have in it? Metal and non-metal, okay? But obviously the presence of a metal is its defining characteristic because molecular compounds only contain non-metals. All right, and there could be 2 or more non-metals, okay? So that's kind of the big difference, but we're also going to look at some behavioral differences between ionic and molecular compounds today. Okay, the big thing here is we want to be able to write the formulae, that's plural for formula, by the way, okay, for chemical compounds, both ionic and molecular, and their proper names, okay, for both ionic and molecular. All right. So, ionic compounds occur when, as we said, a metal from the left side of the periodic table, or the left side of the staircase, okay, bonds with, or reacts with and bonds to a non-metal from the right-hand side of the staircase. Okay? When that happens, we get what's called an ionic bond. Now, ionic bonds are weak. Okay? The reason they're weak is they involve an exchange of electrons, not a sharing. Right? So when a metal reacts with a non-metal, metals tend to give up their electrons, whereas non-metals tend to take them. Okay? There's something about atoms called electronegativity. It's actually one of the things on your periodic table. Okay? So for electronegativity on your guys' periodic table, it is the number right above the symbol. Okay, so for iron, it's like 1.8. Okay, it's actually not on mine here, but okay, on yours, it's the number just above, okay, the small number just above the atomic symbol. Right? So if we're looking at, like for example, sodium and chlorine here, okay, sodium has an electronegativity of 0.9. That's very small. That means it doesn't hold on to electrons well. Okay, it just loses them all the time. Okay. Chlorine, on the other hand, has an electronegativity of 3.2. That's quite high. That means it likes electrons. When it gets them, it holds on to them. Okay, it's like Gollum. All right, it's just never going to let it go. Okay, once it gets one, it's precious. Okay, and so it's never going to let it go. So what happens is when a metal and a non-metal bond, the metal gives up the electron, and the metal or the non-metal takes it. Now, what that does for each one is something Bohr discovered. Okay? We talked about Bohr's model, and he said in Bohr's model you have the nucleus, and for something like sodium here, it's got 11 protons, so we'll just write P equals 11, right? And it's got 12 neutrons, and then it's got its electrons. Now, according to Bohr, and he's right, okay, the first orbital, he's just wrong about the shape, can hold 2 electrons. And the next orbital can hold 8. Okay, and he's also kind of right, kind of wrong about where these go, but it's not really important. Okay, now we're up to 10 electrons. How many are there? 11. Okay. So this last orbital that can hold 12 electrons, or sorry, can hold 8 electrons, only has 1 in it. An atom is always seeking to have its outer shell full. Okay? It becomes very stable and very happy when its outer shell is full of electrons. For sodium, the only way to, there's 2 ways for it to fill its outer shell. Find 7 electrons, or lose 1. What's easier? Lose one. That's why its electronegativity is so low. Way easier to just lose one electron and use the last shell that's already full as your outer shell. Okay? Chlorine is the opposite. Okay? So if we have chlorine, okay, we're looking at 17 protons. We're looking at 17 electrons. Okay, or sorry, 18 neutrons. So we got P equals 17, N equals 18, okay? And then we have 17 electrons. So that means here's 2, okay? All right, that shell can hold 8. It's got 7 in it. If it wants to fill it, it either has to find a home for 7 or pick up 1. What's easier? Pick up 1. That's why its electronegativity is so high. Okay? Once it gets 1, its outer shell is full and it's going to be very happy. All right? So these two get along great. Okay? Because they each have what the other needs. Okay? In order to fill their outer shell. Sodium needs a home for 1 electron. Chlorine's got a spot for 1 electron. Okay? Perfect. So they form an ionic bond. The problem with ionic bonds is they're weak. Because, and don't take this from a sociological perspective, they both got what they wanted. Sounds awful. Okay? But they both got what they wanted, and so now there's no reason for them to stay together. Okay? Yeah, I know. That's what I said. Don't take that from a sociological perspective. This is chemistry. Okay? Not like relationship psychology. Okay? But yeah, now that they have that outer shell full, okay, they'll stay together, but there's lots of things that can split them. Right? For example, when you put salt in water, what does it do? It dissolves. And when ionic compounds dissolve in water, they split into charged particles. All right? So there'll be positively charged sodium ions floating around because they've lost an electron. There'll be negatively charged chlorine atoms floating around because they've gained an electron. Right? This is also why salt water conducts electricity very well. Okay? Distilled water, on the other hand, doesn't conduct electricity at all. Right? It's the presence of the charged particles that makes the solution conductive. That's why you don't want to be in like a swimming pool in a lightning storm. Okay? It's full of ions, okay? Especially chlorine. Okay? And so you don't want to be in there. It'll conduct electricity very, very well. If you were in a swimming pool full of distilled water, I probably still wouldn't take my chances, but okay, it wouldn't conduct electricity nearly as well as pool water. All right. So that's the nature of an ionic bond. So you might want to just add in here as a note somewhere that in ionic bonds, electrons are traded or swapped or something like that, okay, and that the bonds are very weak. Okay, and that's why we have this corny. My name's Bond, ionic bond, and it's taken, not shared. I don't know where I found that, but it's like the corniest science joke ever, but it's awesome. Okay. So electrons are traded, taken, they are not shared. In a covalent molecular bond, which is what happens in a molecular compound, the electrons are shared. Those bonds are really, really strong because they have to stay together. Okay? If they split, neither one will be happy because they were sharing the electron that made them happy. Again, sociological, but it's just an analogy. Okay. Everybody all right with how the ionic compounds work? Okay. Right. When we're naming ionic compounds, okay, the rules are as follows. You write the name of the metal first, and then the name of the nonmetal. And you change the ending of the nonmetal to "ide." And that's it. That's all you have to remember about ionic compounds. Okay? It's the name of the metal and the name of the nonmetal, ending in "ide." Right? So when sodium and chlorine go together, we get sodium chloride. Okay, pretty easy. Okay, but we always name the ionic compound first. Or sorry, the metal first. In the ionic compound, we name the metal first. And I'll catch people on this all the time when we get to chemical reactions. Okay? I'll write the reactions in a different order and people will mess it up. And they'll forget that very simple rule that the metal is always listed first, okay? And the non-metal always second. Okay? And their formulas also written that way. Metal first, non-metal second. And that's just because we're starting from the left and moving to the right. Whatever's on the left goes first. Metals are on the left. Okay, so examples here, we got like magnesium oxide, okay, which would be this, MgO. Sodium fluoride would be NaF. Okay, aluminum sulfide, right, that would be Al2S3. Had to figure that out. Right, I used the charges. Anyone remember how we do that? With the drop and swap, or swap and drop, whichever way your teacher said, it's the same thing. It doesn't matter what order you do it in, the charges will end up on opposite things. Okay, the charge on aluminum is 3+, the charge on sulfur is -2, so dropped and swapped, dropped and swapped. That's how you get the formula. Okay, it was the same for this one. This is a 2+, this is a 2-, so I don't need to write them because they already balance. Okay, it's just about balancing the charges. All compounds also have to be electrically neutral, right? So all the positives and all the negatives have to cancel out or add up to 0. All right, so let's maybe just try a couple here. So remember, we got to remember to name both ions, and this is the other thing. This is a really hard habit for most people to break. A chemical name is a designation. It is not a proper name. Thus, it shouldn't be capitalized unless you are starting a sentence with it. Okay? Sodium chloride is great on French fries. Okay? Then I would capitalize the S. Okay? But other than that, I would not. Okay? It's a chemical designation, so I do not capitalize the name. All right? A true compound should have a net charge of 0. That's what we just talked about. That's the reason for the drop and swap. The example we just had was aluminum sulfide. Okay? And we said that that was, when we do that, we have Al, which is a 3+, and sodium, which is a 2-. So when I take the 2 and put it here, and the 3 and put it here, I have how many negative charges? 6, right? I have 3 sulfur, each one is a -2. So there's a total of 6 negative charges. Every aluminum atom has a charge of +3, and I have 2 of them. 3 times 2 is 6. So it balances out. So the whole purpose of the drop and swap is to not have to do that math. Not that it's hard math, but it's just we can avoid it by just dropping and swapping, and it'll always work out.
So they only bond together if it's going to be electrically neutral?
Yes.
That's the only reason? Okay.
Yeah.
So they have to bond with 2 aluminum and 2 sulfur then?
Exactly, and that's why we don't need prefixes, because there's never any doubt as to the numbers. They can only go together in a certain ratio to be electrically neutral, right? In a molecular compound, because they're sharing the electrons, they could be together in any number, and that's why we have to use prefixes, okay? But we don't use prefixes in ionic compounds because they can only go together one way. All right, so charges are positive on metals, negative on nonmetals, okay, and are equal to the group number, okay? What I mean by that is, okay, this is group 1. Everything in this group has a charge of +1. Everything in this group has a charge of +2, and so on and so on, okay? They actually do the group numbers differently now, but they used to be Roman numerals. This was group 7A, and everything in here was, don't worry about it. We'll just actually take that off because it doesn't make sense anymore because they redid the numbers. Okay. Everybody all right with that? Okay, I want you guys to try, let's just have you do the first 4 for right now. We already did this one, but you can do it again, it's really easy. Okay, so I want you to write the names of these ionic compounds. Okay, I'll give you a couple of minutes and then we'll walk through them together. Okay, so obviously the first one's pretty straightforward because we already talked about that one. Okay, Na stands for sodium. Okay, it's the metal, so it's listed first. Okay, and with chlorine, which I switched to chloride. Okay, so we're looking at sodium chloride, okay, as the name for number 1. For number 2, K stands for potassium. Okay, and F stands for fluorine, right? So we're going to call that fluoride. Okay, potassium fluoride is the name for that one. All right, number 3 has hydrogen and iodine in it. So it will be hydrogen iodide. Okay, now hydrogen's weird. Okay, hydrogen can act as both a metal and as a non-metal. In this case, it's acting as a metal because it's listed first. Okay, if I was looking at this compound, it would be behaving as a non-metal because it's not listed first. Okay, so something you have to watch for with hydrogen, okay, because hydrogen can be, it can act as a metal or a non-metal. It's listed first, it's acting as a metal, and that's most likely an acid of some kind. Okay, this is hydrogen iodide, which is a strong acid. All right, number 4, I've got calcium and bromine. Does it matter that there are 2 bromines? Not for the name, it doesn't, okay, because we don't use prefixes in the names of ionic compounds. Okay. I don't have any capital letters in there, do you? Hey, it's a habit you gotta break. I know it's tough because we always want to capitalize everything. I'm terrible at capitalize stuff all the time. Okay? Just read an email of mine sometime with capital in the middle of a sentence for no reason. Okay? I don't know what, just like look at what big letters. But yeah, we want to make sure that we're not capitalizing any of these. All right, I'm gonna put a few more up here. I want you guys to try. Okay, so I'll give you a few minutes on those. Okay, see how we do. Okay. Probably better I didn't record my rant about that. But, yeah, apparently it's pronounced aluminium now, and you don't have to do that. I won't mark it wrong if you write it the right way. Okay. Next one here, we've got cesium with sulfur. Does the 2 matter? Not for the name. All right, this is just cesium sulfide. Oh, by the way, you can spell sulfide like this or like this, without the capital. See? See how easy that is to screw that up? Because sometimes people spell it P-H-U-R. I'm okay with either. Okay. All right, number 7, we've got sodium with oxygen. Again, the 2 doesn't matter for the name. This is sodium oxide. Okay, we've got barium with selenium, so that will be barium selenide or selenamide. There's actually more than one way to write that too. So you could write it as selenide or selenamide. That's an E in there, selenamide. Sorry, my penmanship needs work, guys. It always has. I just don't put in the time. Okay. Number 9, we've got radium with tellurium, so that'll be radium telluride. Okay, this is lithium fluoride. Okay, we've got rubidium and sulfur. Okay, strontium and iodine, so that'll be strontium iodide. Okay, and then we've got calcium oxide and magnesium selenide. Again, big thing here is just to break the capital letter habit. Okay, when you are writing the names of chemical compounds. Question?
Is this a strontium? There is no N. Am I getting that wrong?
Okay, oh yeah, sorry. Could be strontium. Yeah. I always write it strontium. Yeah, good job. Okay. Any other questions on those? Okay. So, something new that you probably didn't learn about ionic compounds last year has to do with what we call multivalent metals. Okay? Some of the metals in the middle of the periodic table, okay, which we call the transition metals, okay, can have or can lose different numbers of electrons in chemical reactions. Okay? So depending on their electron configuration, they may lose 1 or 2 or 2 or 3, okay, depending on their electron configuration. So the issue here is naming, because from a naming perspective, the chemicals look the same. Okay, their formulas are different. right? But the name would be identical. So example could be, right? If I have iron, and iron is a transition metal or a multivalent metal that can lose 2 or 3 electrons. Now, how do I know that? If I look at my periodic table, okay, the charges are always listed in the top right-hand corner. Right? So you can see if you're looking at beryllium, for example, it is a charge of 2+. Sodium has a charge of 1+. But if I look at iron, it's got 2 listed there, 3 and 2. The most common one is the one listed first. Okay, so the most common charge for iron is 3+, but it can also be 2+. Right? So here's the issue we run into with naming. This is the iron that loses 2 electrons. This is the iron that loses 3. So when they're in a compound with oxygen, the compounds are different. But the names would be the same. That's a problem. Okay? Let's just say, for example, because obviously if they have different formulas, they're going to have different physical and chemical properties. Everyone okay with that? So this is harmless. This is highly poisonous. I'm writing a paper about the benefits of eating rust and getting lots of iron in your body. But I'm talking about this up here, the one that was harmless. I don't remember which one I said was harmless because I'm making this up. But let's just say, okay, that's the situation, because there could be a situation like that. Okay, and I'm talking about you should eat this, you should add it to your diet, sprinkle it on your food, and somebody puts this on their food and dies. Okay, that's a problem. Okay, I mean not for me, but it's a well, it might be because they might sue me. But yeah, it's not good. Okay, they have different physical and chemical properties because they're different compounds. They can't have the same name. I mean, my gosh, if you have a person with the same first name in the same class, it's a problem. Okay. I actually had 2 kids with exactly the same first and last names in the same class once. Okay. I had 2 Chase Andersons. And they weren't related. That was the really weird thing. But they both had the same first and last name. I don't know how many times that screwed me up entering their marks. Okay. Yeah, they had to actually put their middle names on when they handed stuff in. Right? Otherwise, how am I supposed to know whose it is? I don't recognize handwriting. I teach 120 kids. Okay. So, yeah, that's the problem here. I can't have 2 things that are different have the same name. So what we do is we put a Roman numeral in the name to indicate which iron is present. All right. So in this compound, this is the iron with the 2+ charge. So I write iron with a little Roman numeral, like a subscript Roman numeral 2, oxide. This would be iron 3 oxide. Okay. Now, there's one other issue with this. How do I know which one? Like when I just look at a compound, like let's say, for example, I'm looking at this. Copper is also one of these transition metals. It can be a 1+ or a 2+. What is it here? 2+. It's tough though, but here's why. Okay, sulfur always has a charge of what? -2. Okay, if this is going to be electrically neutral, the charge on copper has to be +2. So I kind of have to work backwards in order to figure out which Roman numeral I'm supposed to put in. Right? I can't just reverse the swap and drop. Okay, that's not always going to work either. Okay, because I've had people go, well, just reverse the swap and drop. That'll work about 2/3 of the time. I don't know about you, but I like to be right more than 2/3 of the time. Okay, so what we want to do is we just use the non-metal to figure out what the charge on the metal would be. Okay, and so if we're looking at this one, okay, so this one that we said was iron 3 oxide. Every oxygen has a -2 charge. How many negative charges are there in total? 6. All right, that means I need to get 6 positives from 2 irons. So each iron has to be +3. So there's a little bit of math there. You got to divide one number by another. Okay, not really hard math, but okay, that's how you're going to have to do it. Now I know that this is the iron with the 3 plus charge. This is where people always say, well, I could just reverse the swap and drop. Well, it works on that one, but it didn't work on this one. Okay, so we don't want to do that. Iron 3 oxide. Question?
Could it be Cu2S?
It could be, but then it would be copper 1.
Okay.
Yeah, if it was, yeah, you're right. If it was written like this, okay, this would be copper 1 sulfide. Okay, this is copper 2. Okay, and it's easy to forget to do that. That's the most common mistake that people make when they're naming ionic compounds, is they forget to check for this. If you have a metal that has more than one possible charge, and you can tell that by looking at it on the periodic table, you're going to have to put a Roman numeral in its name.
I'm looking, but is it only in the transition metals that have the Q?
Hydrogen can also be +1 or -1, but yes, generally it's just a mix. Okay, everyone all right with how that works? All right, we're going to practice that a little bit. Okay. All right, so let's just say the first 4 for right now, and see how we do on that. Okay, we already did number 1, so maybe skip that one. Okay, yeah, and we did number 4 as well. So really only doing 2 here, because we've done 1 and 4 already. Okay, so the first one we said we'd already done. Okay, this is going to be iron 3 oxide for this reason. Every oxygen's a -2, which gives me 6 negative charges. Okay, I need to have 6 positives come from the 2 irons, which means that each iron is +3. So this is iron Roman numeral 3 oxide. All right. On this one here, I've got cobalt and sulfur. Sulfur is always a -2. Okay. The 2 possible charges for cobalt are 2 and 3. So which cobalt is this? 2. Okay. So this will be cobalt, Roman numeral 2, sulfide. Right. Everybody okay with how we did that one? All right. And then for number 3, I've got manganese and chlorine. Every chlorine is -1. So there's how many negatives here? 4. Okay. Manganese can have a charge of 2 or 4. In this case, it's going to be 4. Okay, so this will be manganese 4, that's IV, okay, chloride. Okay. If you're not sure about your Roman numerals, watch sequels of any movie. Okay, Star Wars is a good one, goes all the way up to 9, except you don't want to watch 8 because it sucked. Okay. Just terrible. Okay. Just garbage. Okay, absolute garbage. But okay, or Rocky. I mean, there's a lot of Rocky goes up to like 5. You know, anything. Okay. So Roman numerals. Okay, that's if you don't know them, just like it's pretty straightforward. 1, 2, 3, and then 1 before 5, and then 5, and then 1 after 5 is 6, and 2 after 5 is 7. Okay, and that's 8, and then that's 9, and that's 10. You won't need to go past 10 for anything we do. You probably won't need to go past 4 for anything we do. Okay. All right. Then our last one here, we already did this one, copper and sulfur. Sulfur is always a -2, so that means this must be the copper with the 2 plus charge. Okay, so this will be copper, Roman numeral 2, sulfide. Okay. It's not terribly hard to do. What's hard is to remember to do it. Okay, that's what most people forget. All right, let's have you guys try up to number 10 there. See how you do. We'll go over the rest here in a couple of minutes. All right, so for number 5 here, we have tin and we have tellurium. Okay, charge on tellurium is -2. All right, so every tellurium is -2, which gives us 4 negative charges, which means this has to be the tin with the 4 plus charge, because there's only one of it. Okay, so this is going to be tin, IV, telluride. All right, number 6, we've got mercury with astatine. Astatine has a -1 charge. Okay, mercury can be 2 or 4, right? So this is going to be the mercury with the 2+ charge. All right, then we've got polonium with iodine. Iodine's always a -1, so we've got 4 negatives, which means this polonium has to have a charge of 4. Okay, number 8, we've got antimony with sulfur. Okay, sulfur is always a -2, and there are 3 of them. So how many negative charges do I have? 6. Okay, so I need to get 6 positives out of 2 antimony. So antimony must be +3. Incidentally, a lot of these compounds probably don't exist. Okay, I'm just doing this as a naming exercise. All right, so number 9, I've got nickel with nitrogen. Nitrogen's always a -3, so there is a total of 6 negatives. That means there have to be 6 positives, so this is nickel 2. And it's nitride. Okay, so nitrogen becomes nitride, not nitrigide. Something like that. Okay, number 10, we have ruthenium with oxygen. There's 2 oxygens, so that's a total of 4 negative charges. So this has to be ruthenium 4 oxide. All right, everybody okay with that? Make sense? All right, last new thing that can come up with ionic compounds. Okay, and that is that sometimes you'll see something like this. Okay, probably not something you did back in Science 10. This is still what we call a binary ionic compound because it only has 2 parts, but there are 3 different elements in it: copper, sulfur, and oxygen. Okay, now SO4 is commonly known as sulfate. Okay, it's one of the things that can form on like batteries and stuff. Have you ever seen that, like on a car battery? Okay, it starts to get that kind of greenish blue stuff. Okay, that's usually like some type of lead sulfate that starts to form on the anode. Yeah, the bottom of the one, the cathode. Or something like that. Okay. Okay. Yeah. I can't remember. It's been so long.
It is.
Yeah. Okay. Yeah. All right, so we got copper and we got sulfate. Okay, now, how do I know this is sulfate? Why don't I go copper, sulfur, tetraoxide? Because it wouldn't make sense, that's why we don't do it that way. Okay, so on your periodic table, on the top, kind of in the middle there, is what it's called the table of common polyatomic ions. Okay, that is where you will find these special charged particles. Okay? Occasionally, molecular elements will go to, non-metals will kind of combine, but they'll end up charged because there weren't enough electrons to go around. Okay, and they will form these charged particles called polyatomic. That means many atoms, ions. Okay, so polyatomic ions. Right? All we have to be able to do is recognize them. Right? So if I see a compound that has a metal in it, I know automatically it's ionic. But if it has more than 2 elements in it, then I know I have to go to this table and look up the name. So the name of this stuff is copper, and it's actually the copper with the 2+ charge, copper 2 sulfate. And you've probably seen this as little blue crystals. And you probably worked with it in the lab. No? Okay. Because I heard at one point that somebody at JB2 had eaten some. Which wouldn't kill you outright, but it wouldn't make you feel very good either. Okay? Don't eat it. Don't eat stuff from the lab. Okay? It's not good for you. Even if it's sugar, you just don't know what it's been around. Okay? Our sugar sits in the same cupboard as like sulfuric acid. So no, actually that's not true, because that would be really bad. Okay, but yeah, so this stuff is copper 2 sulfate. If I had something like this, what would I call that? Sodium something, yeah. Hydroxide. Okay? All I have to do is look up this thing in that table of polyatomic ions and write down the name. Right? Don't have to change it to anything. This is just sodium hydroxide. This is the active ingredient in oven cleaner. All right, so if you ever smelled oven cleaner, that's what you were smelling.
So if you're doing that, like with the two nonmetals in the middle, do you have to combine their charges and then?
No, actually, in that little chart, they have the charges written beside them. Okay, so sulfate will have like it'll be like 2 minus beside it.
Okay, so it'll already be combined for you? If you look at
Yes, it's already, yeah, that's the charge of that ion. That ion doesn't split apart. Okay, it stays together. All right, everyone okay with that? So that's something different. You probably didn't do that before, but it's not something terribly difficult either. You treat these like you would any other non-metal when we're naming, except you don't change them to "ide." You just write their name as it appears in there. Okay, the charges swap and drop the same way. One thing that can happen with a polyatomic ion is this. Okay, when these two things go together, right, the charge on hydroxide is -1. The charge on magnesium is +2. If I drop and swap, I get MgOH2, but that's not right. Because this is saying there's 1 magnesium, 1 oxygen, and 2 hydrogens. I want this to say that there are 2 hydroxides. So I have to put it in brackets. Just like math, right? If I put something in brackets, the number beside it applies to everything in the brackets. It's the same. Okay. What's that? It is smart. Sometimes those physics or those chemistry guys come up with good things. All right. So that's just little things here or there, things that you didn't learn before, but they're the little things that we add on in Science 10. Okay? Just little things for you to remember here or there. We'll have time to practice all that, so you don't need to worry too much right now. Okay, I think I had more on here. Okay. What time is it? Okay, so just quick review here, and that's probably all we'll have time for. Just a quick review of the molecular compounds. We won't get to naming them today, okay? But we'll just talk about them here. So for molecular compounds, we get a molecular compound when 2 nonmetals join together. The difference, we kind of talked about this earlier, between an ionic compound and a molecular compound is the nature of the bond. Okay? An ionic bond is weak because the electrons are traded or taken. Okay? They're not shared. But in a covalent molecular bond, covalent meaning sharing the valence, okay, sharing the electron, okay, is much stronger. In order for both of these things to have a full outer shell, they have to share the electron. If they split, neither one will be happy. Okay, so if we're looking at water, for example, okay, that's what this is here on the left, okay, water, okay, has oxygen, 1 oxygen, and 2 hydrogens. Question?
What would happen if they split?
They would keep their electrons,
Yeah.
and they wouldn't have full outer shells. So they would go back to their regular elemental form. They wouldn't become ions, right? They would just go back to their regular elemental form and not be happy. Okay, so they're really happy when they're here. Okay, no, that's personification or non-English. I think that's right. Okay, but they're really happy, okay, when they have this full outer shell. Okay, for hydrogen to have a full outer shell, it needs 1 more electron. Well, it gets it from oxygen. Oxygen needs 2 more electrons to have a full outer shell. So it bonds with 2 hydrogens. Now it's happy too, but they're only happy as long as they're together. As soon as they split, then oxygen's missing 2 electrons, hydrogen's missing an electron, and they don't have full outer shells. So these bonds are very, very strong. Okay? Molecular bonds are very, very strong compared to ionic compounds because of that shared electron.
Would both hydrogen atoms have to combine with the oxygen at the same time?
Yes. Now, that's what we were saying. Remember just a minute ago we talked about this ion?
Oh, yeah.
That's what happens when we don't get that other hydrogen, right? We've got this hydrogen that's there, this oxygen that's there, but we've got that extra electron now, but it's not working. Right? We lost that other hydrogen, so now our charged particle is not happening. Okay, so nonmetals usually have negative charges. No one element gets to keep the electrons. They share them, okay, and that's the covalent bond. The other thing is, because they're sharing them, there's not going to be any dropping and swapping, okay? The charges are balanced, but they're balanced because they're shared, not because they're traded. So we don't use the drop and swap, and we have to use what in the name? Prefixes. Because now their arrangement, their ratio is not predetermined, okay? There could be any number of any type of atom in a molecular compound, so we have to use prefixes to tell people there's this many oxygen, there's this many sulfurs or whatever. Okay, so we'll talk more about that, okay, tomorrow. Now, on Thursday of this week, you will have a quiz. So you didn't have one today because it was after a long weekend, but we did talk about that every Tuesday, every Thursday. I will post that quiz tomorrow, okay, by the end of the day.